So let's revisit springs. We've talked about work done by springs in the last lecture. Here we have a spring that is not being compressed, nor is it being stretched. It's at its initial position of x is equal to 0. And we can recall that the work done by a spring is going to be equal to 1/2 multiplied by the spring constant multiplied by its distance from the unstretched state squared. Here it is at its unstretched state, so no work is being done by the spring. If we take this block and we stretch it over some distance right there, the spring is pulling backwards on the block. The force of the spring, you know intuitively, is in that direction, which is the opposite direction as motion. So the spring is doing negative work on the block, and as the spring relaxes, as you let it go ahead and pull the block back towards the origin, that's where it wants to go. Now it's doing positive work because the spring is, the direction of the motion of the block is in the same direction as the force of the spring. And as the spring is compressed, you know that it's going to be pushing backwards on the block. And if you compress a spring and you let the block go, then the spring is going to have a force that is in the same direction as this position vector right here. So a compressed spring that is unwinding is doing positive work on the block as it relaxes. So springs are going to be doing positive work when they relax, when they're returning to their natural state. We can talk about the energy that's involved for a spring. This is going to be another type of potential energy. It's going to be the elastic potential energy, and pretty much any body that is elastic is going to return to its original shape after being deformed. This is true for springs. It's also true for many other bodies. I will say that there are limits, and if you've ever played with a slinky, which is essentially a spring, you know that if you stretch it too far, it will never go back to its original shape. But for this class, we're not stretching springs past their deformation point, where they'll never return to the original shape. What's being stored in a spring is I've already mentioned, elastic potential energy, and it is storing this energy such that it can be used later. If you compress a spring and you put a ball on the end, then that ball can be launched at some velocity, so it has the potential to increase an object's speed. So by my definition of potential energy, compressing a spring is indeed potential energy. We know that work and energy have been related for kinetic energy and for gravitational energy. It's not going to surprise you at all that the work you do on a spring is going to be related to the potential energy that it can store. Remembering what we know about work, we can write the potential energy stored in a spring to be 1/2 kx squared. And the interesting thing about this is if we take a look at the graph of the elastic potential energy right here, it doesn't matter whether the spring is being stretched or whether it's being compressed. Energy is being stored in it for both directions of motions. That intuitively makes sense, because if you stretch a rubber band or something like that, you know that it can shoot across the room. If you compress a spring, you know that it can pop back up. If we have situations where there's both gravitational and elastic forces, it turns out that we can write the total potential energy of the system, this big capital U, to be equal to the sum of the gravitational plus the elastic potential energies. And I can actually expand on the topic I was talking about earlier, where I said if gravity is the only force acting on a system, and rewrite the energy to be equal to the kinetic energy plus the potential energy, and I said that that must always be a constant regardless of where you are in a situation. Before that, this U right here was just gravitational potential energy, but it is also true if there is elastic potential energy in a system. So energy will be conserved if the only forces that are acting on a problem are gravity and springs. Taking into an example, this girl jumping on a spring or on a trampoline, at the very tippy top, all she has is not kinetic energy, all she has is potential energy. She has the ability to fall down. She's not moving upwards. Her velocity is equal to 0 at the very tippy top, and there is no spring force acting on her. As she's falling down, falling down, and falling down, she's gaining kinetic energy. She's losing potential energy, so her potential energy is getting smaller. And then when she is bottomed out on the spring, I'm going to make sure I write U gravity right here. When she's bottomed out on the spring, all she has is elastic potential energy from the spring. That potential energy in a frictionless surface will propel her directly back up to the same height that she started at. So the energy here must be equal to the energy here, must be equal to the energy at the very bottom. And we can use this to our advantage when we're solving problems where if we know how far a spring has been stretched, we can write out how fast it should be going at the point where there's no gravitational potential energy, or we could figure out how high an object has gone simply by using this principle. This problem right here is an excellent example of that, where in this example we have stretched a spring out to point 1. Let's go ahead and write the energy at point 1. The spring has been stretched out to some distance, so we know that it's going to have some spring energy, and it is not moving, so it has kinetic, or I'm going to write the kinetic energy on here, but I'm going to say that the kinetic energy is going to be equal to 0. The energy at point 1 is simply going to be 1/2 k x squared. The book has a nice little drawing of this, where all of the energy of the system is equal to the elastic energy, and then the ball, then it is released, and at point 2 the spring is still stretched a little bit. The total energy of the system, energy at 2, is going to be identical. The energy at 1 is equal to the energy at 2. Now at this point we have some elastic potential energy and we have some kinetic energy. I'm just going to put a 1 on there. What we can do is we can say, okay, well, we know that this is 1/2 k and now x2 squared, and then 1/2 m v2 squared. The 2 just says we're at point 2. We can relate these two guys. We can set the top one equal to the bottom one, and now we can go ahead and solve for velocity, given that we know this position and that position. So in your notes, finish working through this problem. Solve for velocity. Be comfortable with that coming into class. If we have a system that has two potential energies and friction, we can no longer write that the kinetic energy at point 1 plus the potential energy at point 2 at point 1 is going to be equal to the kinetic energy at point 2 plus the potential energy at point 2, where here these potential energies are due to both springs as well as gravity. Now we have to worry about this little bugger called friction. What friction is going to do is friction is going to do work. So we would write our kinetic energy plus our potential energy plus the work done by other things. This work can be due to friction, it can be due to a person, it can be due to anything. Now the sum of these three guys will be equal to the kinetic energy plus the potential energy at a second point. Example 7.9 is an excellent way to highlight that. If we consider an elevator shaft that's being tested and we're interested in the spring constant of the elevator shaft, the safety spring if you will, we have the elevator moving downwards at 4 meters per second at point 1. I'm going to define at point 1, that's going to be my 0 point, just for the sake of argument. So at point 1, the spring has not been compressed. I have no spring energy. I have no potential energy. I'm calling that my 0 point. All I have is kinetic energy. That's all I have at point 1. Now if I consider a little bit later where I've traveled down some distance y, I've compressed the spring, but I'm no longer moving. At point number 2, I'm going to obviously have some spring energy, and I'm also no longer at my 0 point, so I'm going to have some gravitational potential energy as well. It's going to be negative because I am below my starting point, but that's okay. The numbers will work themselves out. I could have just as easily defined my 0 point to be right down here, and up here I would have written some potential energy due to gravity in point 1. So what I can now do is I can say I'm going to have some initial kinetic energy at point 1. I have 0 potential energies to add in. I do now also need to worry about the frictional force. That frictional force is going to do some work, knowing that work is going to be the force multiplied by the distance that it travels. Simply going to write that as work for right now. That's going to end up being equal to the gravitational potential energy plus the spring potential energy. And at this point, I know my velocity. I can calculate my kinetic energy, 1/2 mv squared. I know what my work is. I know my frictional force, and I know how far it acts for. I know my gravitational force. I know mass times gravity times this distance y. I can now solve for how much potential energy went into the spring, and if I know how far it was compressed, I can go ahead and calculate my spring constant. I expect you to work this problem. I expect you to come to class understanding this problem. So this leads us to finally getting around to defining conservative and non-conservative forces. If there are only conservative forces in the system, then we can say that energy is always going to be conserved and is always going to slosh between kinetic energy and potential energy. We've talked about the conservative forces of gravity and spring force, and if there are only conservative forces, then we can say that the energy at one point must be equal to the energy at a second point. So what 4 things can we say about the work that's done between 2 points of a conservative force? Let me first start off with B, and I'll get back to A. Is the process is reversible. If we consider a ball where we take that ball and we lift it up, then you're doing work to the ball. When the ball comes back down, and gravity is doing negative work, when the ball comes back down, now gravity is doing positive work, and it's going to be equal to the amount of work that gravity opposed on the way up. So that system is reversible. It's independent of the path between 2 points. We've already shown that on a previous slide. And it's going to be 0 if the starting point and ending points are the same. What that really means is if you take a ball and you lift it up, you've done some work to it, if you bring it back down to the finishing point, then the work that the ball has done to you is going to be equal and opposite in magnitude to where it started. Thinking about solely the gravity force, U is equal to mass times gravity times y. If the starting point is the same as the finishing point, then no work there has been no energy changed. So the work can be expressed as a potential energy function. What that really means is the work is going to be equal to the change in energy of the system. For forces that are non-conservative, perfect example would be friction, then we say that these forces are non-conservative forces, and in that case we can no longer write the energy at 1 is going to be equal to the energy at 2. These forces, friction, they do work. So we have to say that the energy at 1 plus the work that was done by the system is going to be equal to the energy at 2. If that work was negative, then the energy at 2 is going to be lower than the energy at 1. Just to show you that frictional work depends on path, therefore it must be a non-conservative force, if we consider moving this futon from point 1 to point 2, and we go about it in a roundabout fashion where the distance that I travel is going to be 3.5 meters, I know that the work that I've done is equal to my frictional force multiplied by my distance. In this case it would be 3.5 meters. If I take maybe a more direct route and I take the 2.5 meter path and push the table out of the way, then the work that I'm going to do is going to be equal to the force multiplied by the distance. That's still the same. The frictional force is still going to be the same. The coefficient of friction between the futon and the carpet's going to be the same, and the normal force of the futon is going to be the same. But now my distance is equal to 2.5 meters. So you can see that the work done depends on the path that you took. Therefore, friction is a non-conservative force. Example 7.11 shows you how to determine whether a force is conservative or non-conservative. You know that if an object starts and finishes at the same location, that if it is conservative, then there should be no work done. The energy should be the same. So if we consider this particle traveling along leg 1, we know that work is equal to the force dotted with the distance that it travels. Here the force is perpendicular to the distance that it's traveling, so we can say that the work must be equal to 0. Over here the force is in the same distance as the direction of motion, so we know that the work is going to be present, and the book shows you how to go about calculating that. It's going to end up to being CL squared. Over here is the same as the bottom. The force is perpendicular to the distance that we're traveling, so the work is going to be equal to 0. And over here we have no force, so again the work is going to be equal to 0. So here I've gone around my complete path. I've ended up where I have finished, but my net work is going to be CL squared. So there was some net work done. This force must be non-conservative. Now let's talk a little bit about the conservation of energy. Very important concept. It turns out that I've been a little bit loose in my definition, mainly because the book has been. Non-conservative forces do not store potential energy. You cannot, or friction, for example, is not going to store any energy. It's going to, well, in a sense, say you can say waste energy, it's going to change the internal energy of the system. So the work that was done by other forces, for example friction, is actually going to change the internal energy of a system. Energy is actually always conserved. It cannot be created, it cannot be destroyed. It only changes form. Very important concept. So we can write the energy at one point is going to be equal to the energy at another point. However, we have to write these energies to be equal to the kinetic energies plus the potential energies, which is going to be gravity plus the elastic, plus the internal energy of the system. Since energy 1 will be equal to energy 2, we can also write this as a delta, the change in kinetic energy plus the change in potential energy plus the change in internal energy of the system must be equal to 0. Very, very, very important concept for this class. You might be saying to yourself, well, what is this internal energy of the system? Most of the time, if we're talking about friction, then we're talking about heat. We're talking about thermal energy. So the work that was done by friction goes into thermal energy. So that's what this delta U is most likely going to be. Now here's a little bit of calculus just to wake you up. We can write the force as the negative derivative of the potential energy function. For example, if we write the potential energy of a spring to be 1/2 kx squared, and we take the derivative with respect to x, take the derivative, you see that right here, we're going to end up with negative kx. That is the force that is from a spring. Similarly, if we look at the gravitational potential energy, and we take the negative derivative of that with respect to, in this case, it's going to be y, not x. We do that, we end up with negative mg. That is the force that is due to gravity. And it turns out that if we have a function describing our potential energy, u is equal to some function of x and y, then what we can do is we can take the derivative, the partial derivative of u with respect to x, put a negative sign on there, get the force in the x direction, do the same thing for the y direction, and get the force on y. For energy diagrams, what we're really doing is we're looking at what I've been talking about graphically this whole time. If we consider a cart on a spring that is oscillating back and forth, if the cart is way over here and it has stretched the spring out completely, it has all spring energy. When the spring is not compressed, it has all kinetic energy, and when the spring is all the way compressed, again, it has no kinetic energy, it has all spring energy. We know that we can graphically draw the spring energy with that parabola, u is equal to 1/2 kx squared, and we know that the total energy of the system must be equal to a constant. That's going to be its kinetic energy plus its potential energy. So we can say that the sum of the potential energy and the kinetic energy at any given point must add up to this big energy line. Diagrams like this become much more useful in higher level physics, such as quantum physics, when you're looking at particles trapped in wells and so on and so forth. The last thing I want to talk about with potential energy functions is if we're looking at a graphical representation of the potential energy, if we look at the slope or the derivative of that guy, that tells us something about the force, remembering that the force is going to be equal to the negative derivative with respect to x. What that's really saying is that's equal to the negative slope if you haven't yet seen this in calculus. So right here it is sloping downwards. That tells you that the force is going to be positive. When the slope is equal to 0 at these points right here, then the force is going to be equal to 0, and really just the slope is going to give you the force.